Okay, so we are live now. Thank you everyone for joining in. We have Jayadithya with us, who will be presenting his talk, and then we have also Oishi and Raghunath with us. Thank you for joining in. So, Jayadithya, can you introduce yourself?
My name is Jayadithya Gupta. I'm a class 10 student from Mumbai. I was a part of the Cheenta Research Summer Program this year, and I was a part of the hyperbolic geometry group. And today my talk will be on Hurwitz investigations and group diagrams.
Thank you very much. We are excited to hear what you have to say. So, all the best.
So next. Yeah. So before I start, I'll just give you an overview of what we will be covering in the presentation. Firstly, we will look at Euler's characteristic equation and the proof of Euler's characteristic equation. We will also look at a brief introduction to group diagrams, and then we will delve deep into Hurwitz investigations. So we begin with Euler's characteristic equation. So Euler proposed a theorem that stated that in a surface of genus P, if it is divided into a number of regions by marking vertices on the surface, and the vertices are then joined by closed arcs, then V minus E plus F is 2 minus 2P, where V is the number of vertices, E is the number of edges, and F is the number of faces. We call the number 2 minus 2P the Euler characteristic of the surface. So let's proceed with the proof of Euler's characteristic equation. Now, the underlying assumption in the proof is that the formula holds true for a sphere. And this formula actually agrees with a sphere because the genus of a sphere is 0. And substituting 0 in the equation gives V minus E plus F is equal to 2. So we assume that V minus E plus F is equal to 2 for a sphere to proceed with the proof. Okay, so could you go to the next slide? Yeah. So I wanted to begin with a more specific case. We'll show the proof first for a double torus and then a surface of any genus. So a double torus has a genus 2, which means that the maximum number of cuts you can make in a genus along the non-intersecting loop so that the surface would still be a connected surface is 2. What we will do is we will cut the torus along its 2 loops so that we end up with the second figure. Then we will paste another face on each of the cuts. So essentially we are making 2 cuts and then we are pasting 4 faces on each of the cuts. Now notice that the second figure, the resultant figure that we get, is a surface with genus 0. If the genus was to be greater than 0, that would mean that we could make another cut along the non-intersecting loops, but that would mean that the genus of a double torus is greater than 2, which is a contradiction. And so the genus of the resultant figure is 0. Now think of this figure as a clay model. If it is a clay model, we can compress it so that it forms the third figure, which is just a cylinder. And we know that a cylinder can be transformed into a sphere. And because we knew that the formula holds true for a sphere, that is V minus E plus F is equal to 2 after adding the 4 extra faces, for the original surface, the formula was V minus E plus F is equal to 2 minus 2 into 2, which is minus 2. And now we'll show the proof for a general case. Now could you go to the previous one? Yeah. So we consider a surface with genus P and make P cuts along each of the P loops. So that, and then we attach 2P extra faces to each of the P cuts. Now the resultant figure has genus 0. And we know that because the resultant figure has genus 0, it can be transformed into a sphere. And during such a transformation, V, E, and F will remain invariant. Yeah. The next one. Yeah. And we know that by the assumption v minus e plus f is equal to 2. But this 2 is obtained on adding the extra 2p faces. So for the original figure, we must subtract the 2p faces, which is how we get v minus e plus f is equal to 2 minus 2p. And this concludes the proof for Euler's characteristic equation. Yeah. Okay, so the next thing that we'll be talking about are group diagrams. Yeah. So firstly, what are group diagrams? Group diagrams are figures that show a one-to-one correspondence between the group elements and the vertices and the generators and edges. And they display all possible relations between the elements of the group. And these figures are called group diagrams. In other words, it shows the relation between the different elements of the group and how each element can be obtained from another element by applying a combination of the generators. So now we will look at the group diagram of S of 3, which just represents a permutation of 3 elements. This is defined by the generators S1 and S2, and the relations S1 square is S2 cube, which is equal to S1 S2 square, which is 1. Okay, so this gives us the resultant group diagram. Now, if we notice this group diagram, so basically, out of for every vertex, there is an edge of S2 going outwards, there is an edge of S2 coming inwards, and there is an undirected edge of S1. We can also notice that there is a triangle formed by the S2s in the inner part of the diagram. That is because if we apply S2 3 times, we land back to the same element. Similarly, there is an undirected edge of S1 because if we just apply S1 twice, we land back at the same element. And yeah, that's how you obtain the group diagram for S of 3. Right. So that was all about group diagrams. Now we look at the main topic for today, which is Hurwitz investigations. Yeah. So let S1, S2, S3 till Sn be the generators of a finite group. Then we will introduce a new generator Sn plus 1 by the relation the product of the generators is 1. And this relation S1 Si raised to mi is 1, where each mi is a finite integer. Now the purpose of introducing a new generator Sn plus 1 is because we want to perform some analysis on which is the relation between the genus and the number of elements of the group. And to perform that analysis, we need the first relation, that is the product of the generators is 1, which is why we introduce a new generator Sn plus 1. Okay, so now let's take a look at the group diagram for the Hurwitz for the formed by the generators. The group diagram will be an M1 gon, each with edges S1, and M2 gon with edges S2, and so on. And between any two consecutive polygons, there will be an n plus 1 sided polygon with edges S1, S2 till Sn plus 1, whose two edges at a given vertex are shared with the neighboring polygons. So let's take a look at the group diagram. Yeah, so this is how the group diagram would look. Now, the mi-sided polygon is obtained from the relation Si raised to mi is equal to 1. That is why we have an M1-sided polygon, M2-sided polygon, M3-sided polygon, and so on. The reason we have an n plus 1-sided polygon is because of the relation that the product of the generators is 1. All right. Another thing that, no, nothing was space. Yeah. Another thing that we should note is that the reason why we have so many n plus 1 loops is because they're all different. All the n plus 1 loops are different. For example, in the first n plus 1 sided loop, Sn, the vertex Sn is attached to the edge Sn is attached to the vertex A. In the second n plus 1 loop, the vertex S1 is attached to A. In the third n plus 1th loop, the edge S2 is attached to A, and so on. And that's why all the n plus 1 sided polygons are different. Another thing is that we cannot obtain such a group diagram in the Euclidean plane. This is because if you compute the sum of the central angles, they add up to more than 360 degrees. which could not be possible in the Euclidean plane. This brings up the need for another plane, and that's why we use the hyperbolic plane. Now, in a plane other than the Euclidean plane, the angles of a polygon can go to any arbitrarily small value, and that's why it is very useful to use a hyperbolic plane in such a case. Yeah. Now we take a look at the number of edges and the number of faces in the group diagram. So to calculate the number of edges, we notice that we calculate the degree at each vertex. Now there is one edge of SY coming into each vertex and one edge of SI going out of the vertex. And this is true for each of the n+1 vertices, which is why the degree at each vertex is 2 into n+1. Now there are n different elements in my group. So the total sum of the degree would be 2 into capital N into n+1. And that's why the number of edges, which is half the sum of the degrees, is half of 2 times capital N times n+1, which is just capital N into n+1. And for the number of for the number of faces, we notice that if we apply the generator ISI-CMI times, we come back to the same element. So the group action just creates a subdivision of the surface with n by mi different faces. And the identity, the n+1 sided polygon, so there are n+1 sided polygons for each vertex, which would create a total of n into n+1 faces. But we are overcounting this by a multiple of n+1, which is why the total number of faces that we would add is just n into n+1 by n+1, which is n. And this gives us the total number of faces, which is just n into 1 plus sigma I going from 1 to n+1, 1 by mi. Yeah. Okay, so now we just substitute these values into Euler's characteristic equation and just perform some manipulations, and we get the final result, which is this just follows by taking n common and multiplying the entire equation by -1. Yeah. So now we want to establish some kind of a relation between the genus of the surface and the number of elements in the group diagram. And this is done by carefully analyzing each case. Now there are 3 claims. We'll be proving 2 out of them. So if n is greater than 3, then p is greater than equal to 1 plus n by 4. If n is equal to 3, then p is greater than equal to 1 plus n by 12. And if n is equal to 2, then p is greater than equal to 1 plus n by 84. And the underlying assumption in this case is that the genus of the surface is greater than 1, that is p is greater than 1. Okay, so now let's take a look at the case when n is greater than 3. So we just substitute all the values into Euler's characteristic equation, and we notice that each mi has to be greater than equal to 2. So we get that 1 minus 1 by mi is greater than equal to 2. Thus, we end up with 2p minus 2 is greater than equal to n into n minus 3 by 2. And because n is greater than 3, this is just greater than equal to n by 2. And just some substitutions show us that p is greater than equal to 1 plus n by 4. The next case is when n is equal to 3. Again, we perform similar substitutions. And here we notice that if all the mi's are equal to 2, then we would get p equal to 1, which is a contradiction to p being greater than 1. So one of the mi's must be greater than equal to 3. Then performing all these substitutions gives us that p should be greater than equal to 1 plus n by 12. Okay, and the case for n equal to 2 follows similarly. We just perform an analysis for 3 different cases, and we get that p would be greater than equal to 1 plus n by 84. Great. So that was the case when the genus of the surface is greater than 1. We will now be looking at the case when the genus of the surface is equal to 0. So if the genus of the surface is equal to 0, we just substitute these values and we get that the sum of 1 minus 1 by mi is 2 minus 2 by n. Okay, and also notice that since each mi is greater than equal to 2, this is 2 minus 2 by n has to be greater than equal to n plus 1 by 2. A series of simple manipulations then shows that n has to be less than equal to 2, which shows that the only possible values of n being an integer, is 1 or 2. Okay, and I will conclude with the case when n is equal to 1. So if n is equal to 1, then we just again substitute the values into the equation. We get 1 by m1 plus 1 by m2 is equal to 2 by n. If we assume that m1 is less than equal to m2, then we get that m1 is less than equal to n is less than equal to m2. But the interesting part is the group must contain at least m2 elements, right? Which shows that n has to be greater than equal to m2, which is possible only if n is equal to m2. And then substituting that shows us that m1 is equal to m2. So the group is then defined by the relation s1 raised to n is equal to s2 raised to n is equal to s1 s2 is equal to 1. And the group diagram that is constructed using these relations is then called the cyclic group or the polygon group. So let's take a look at the group diagram. Now let us take a look at the example when n is equal to 7. Now because s1 to the power 7 is equal, when s1 is applied 7 times, we land back to the identity element. We would need to construct a septagon. Similarly for s2. And because we apply s2, because when we apply s1 followed by s2, we again come back to the same element. S1 and s2 are in opposite directions here. And to conclude, I would like to tell you all about a problem that we are solving as of now, which is called the word problem. And this is the base to solving the word problem. The word problem actually determines whether or not two elements in a group are equal. And it is not easy to determine the sufficient relations between the generators of a group. But if we had the sufficient relation between the generators, then it would be very easy to determine whether or not two elements are equal, which is why using group diagrams and the relation between the genus and the number of elements helps us in solving the word problem. Another very interesting thing is that we began with a geometric relation, that is Euler's characteristic equation, and we finally ended up with an algebraic result about the cyclic groups, which is the s1 raised to n is equal to s2 raised to n is equal to s1 s2. So through this presentation, we've actually managed to establish a connection between geometry and algebra. And I really hope you like this presentation. And I would really like to thank Ashani sir and Raghunath sir for giving me the opportunity to present.
Thank you. Thank you so much, Aditya. It was a really nice presentation from your end. I would also like to take some questions. So, if any one of our audiences is having any questions, you can definitely email it to us at support@cheenta.com, or you also can comment it down in this YouTube live or Facebook live that's going on, and we will then comment it back later. Okay. So yeah, so for now we can end this session here. Raghunath sir, do you have anything to tell at this moment?
No, the presentation was really beautiful, and I hope we will also have more presentations related to the dense word problem. So all this culminates to exposition of the dense word problem, and let's see how follow the series of these lectures to get to know how we try to understand the final solution to the word problem by them. Yeah.
Okay, all right, sure. We will definitely have more presentations on this on the topics. Okay then, thank you so much. Thank you so much, Aditya, Raghunath sir, and also the audience who are actually on the live and watching us. We will definitely meet again soon.
Thank you so much.
Bye.